Ah, Amy. Huh? Taxi? Hexagon? What an hexagon? Hexagon? Hi, check. Gina, all the things. Morning, students.
Sir, good morning, sir. This is Suresh.
Good morning, Professor student.
Sure. Sir, yeah, I just again sent a reminder message to students, sir. They will join for another 2 minutes.
Yeah,
Yeah, yeah.
silence.
So, shall we wait for 2 more minutes, sir?
Sure.
Yeah, yeah. Thank you, sir.
So good morning to all those who joined us today. Let me know, guys, when you would like me to start the session. All right, start.
Dear students, please inform others to join immediately. Sir is waiting. Dear students, please inform others to join immediately. I can see only 28 members. Sir, I think we can start the session, sir.
Okay. All right. Good morning, everyone. Good morning, all students. Good morning. It's student. So let's get started. So, most of you, pretty much all of you were there yesterday. So I'm hoping most of you who attended yesterday's session, got the concept, understood the concept of support electric machines, and most importantly, the fundamental behind this concept of optimization, that is the margin between the support vectors and then deriving the constrained optimization problem to solve for the Hasini Reti, RGB Hasini Reti. Hasini, you have any question or you want to say something? Hasini? Can you unmute and speak if you have to say something? I guess it's very stiff, so you can continue. So we learned about optimization problem, final problem. So let's today recap and recap the entire content that we went through for SVM and focus more on the implementation step by step, line by line. Okay, good to go. So we have it on the 36 students. So that's nothing very confusing. So I hope there is no noise behind me. You guys can hear me clearly. Professor Suresh, there is no issue with my audio, right?
Sir, please tell me, sir.
There is no issue with my audio, right?
No, sir, it's clear, sir. It's very clear.
Okay, excellent. All right, so let's recap the SVM. Yes, SVM is essentially for classifying data into classes or categorizing data into classes based on the latent or hidden pattern, data pattern. The pattern can be any pattern could be, similar data on one side and other similar data, another similar data on the side, is linear, or it could be, non-linear with some sort of irregular boundary of classification, as we have seen in this, right, in this picture generated by ChatGPT for the classification. The data, if we take an approximate boundary of data, colored shapes. All shapes are same, but blue ones and the red ones, right? The blue and the red. So essentially, SVM is for classification, or in other words, we would like to have in real world classifying data based on the latent characteristics of the data. Could be one or could be many. Could be linear, could be non-linear. Would be helpful in many business cases in real world. We talked about spam code, we talked about disease detection, we talked about the automation of identifying received email as spam or not spam. Most of you might have experience with this in Gmail, right? And also identifying based on the latent characteristics into various categories of customers, which will help target the marketing expenses, marketing budget to generate more meaningful revenues for a particular product or product category, right? So we looked at all those business use cases or real world use cases of classifying data with linear or non-linear. to be able to decide whether a person is credit worthy to grant a loan or a particular credit card transaction is a genuine transaction or a fraudulent transaction. Right? So classification can occur, can be, in one hand, be categorized into based on the outcomes into two categories: binary classification and multi-phenomenal classification, where the inferences can be more than two categories. In the case of multi-phenomenal classification, and in the case of binary classification, as in the case, it would be outcomes could be outcomes are two, and then the prediction has to be one of the two. And also, yeah, I'm class. I mean, based on the characteristics of the data or the separability of the data based on the latent characteristics in the provided data set or available data sample. If those classes of data can be separated linearly using a line or bunch of lines, and then we call it linear classifier, or if it is separated, it's not possible to separate linearly, but we have some sort of non-linear curves, or it could be hyperplane, non-linear curves in more than 3 dimensions. Then we call it classification, non-linear classifier. Also looked at some of the methods or the algorithms that are developed for this purpose. We all went through also. Naive days, probably will be looking at some of these naive days and computer that I believe we are figuring that out, especially conclude on this. We also looked at some examples and characteristics of these, or we looked at the contradictions and comparisons of linear and non-linear classifier. We also looked at the key components of comparison, particularly the 2 to 3 points. All of these, depending on end of the day in business, when technology is used in business, what matters at the most to the owner of the business or for the meaningful existence of the business is what is it that is being built and how much does that cost and how quickly can that be built. So if you look in those 3 lenses, what are the key metrics that we need to look at to compare these linear, non-linear classification algorithms is how difficult it is to create a mathematical formula or derive a mathematical formula for decision boundary. Obviously, if it is a linear straight line, it's relatively easier to derive a mathematical formula for a straight line, which is, a transpose and so rings, x bar, x I bar, x bar, right? Plus some mass intercept. So how difficult is it to create that boundary? And from that difficult comes the performance. From that difficulty comes the performance, or from that difficulty we can derive the performance and cost. Performance is nothing but, in a way, it's a very generic polymorphic term. Performance essentially indicates the multitude of metrics that we will be talking about pretty shortly: accuracy and the speed at which algorithms can be trained and that prediction can take place. Right? We don't want, obviously, to predict, given one sample to predict it takes 10 hours. That's not highly performant. At the same time, while it may take a few milliseconds to predict given one sample, they are 10 hours. But to train that algorithm, if it takes 10 days, 20 days, again, it's not reasonably performant. Right? So performance, and of course, the derived factor from all of this is the computational cost. So how long it takes to run. Um, Essentially, the cost is directly proportional to the computation involved. So the computation is to train, computation is to predict the entire cost. And if we are talking about millions of data sets, which in some cases may be needed.
Excuse me, sir. Sorry to interrupt.
Yeah.
Students, everyone, please mute yourself. We are getting some sort of disturbance. Please mute yourself.
I think that it could be from my side.
Oh,
I had
okay, sir. Okay, sir.
one
Okay,
of
sir.
our neighbors.
Yeah.
You guys can hear me clearly, right?
Yeah, your voice is clear, sir. Yeah, please go ahead, sir. Thank you.
So the computational cost is today what matters. Computing, the computers have become commodity today. Right? Today, sitting probably in a village near to GPREC, let's say, I don't know, Zone, it's not known in the village. Any village, Teku probably. And if you have a 4G connectivity, you can spin out tens and twenties or hundreds of elastic EC tools on Amazon or virtual instances on Google Cloud. And you can schedule any job, you can get any job computed or executed by this machine. So it has become a commodity. Essentially, commodity is a term used to indicate that everybody buys it, not only few people buy it. And it is affordable by pretty much everybody. Right? So even though it is a commodity, obviously, buying, let's say, what is the most expensive thing? Probably oil today. Right? Oil is not an example. Anything, for example, maybe rice. Right? It may not be that expensive, but we don't want to keep buying a lot of rice. We want to control it. Right? Price is a commodity. The same way, computing is a commodity. And we want to restrict the use of that, meaning with minimal computational cost, we want to train and predict anything that we want to accomplish in a given business. So these are the three parameters, and considering these three parameters, obviously, it is contextual, but obviously linear classifiers will definitely be a little cheaper and maybe performing better. But they have a constraint that they can classify with non-linear data, and they will be. So it's situational. We will look at that. We also looked at the mathematical derivation and intuitive visualization of decision boundaries, be it linear, non-linear, be it in 2 dimensions or 3 dimensions, and expressing the decision boundaries mathematically if it is linear, and if it is 2-dimensional, this, and if it is dimensional, this equation is nothing but weights vector transpose. So dot product of the weight vector and your any given input. And if it is non-linear, how we can separate it by transforming using kernel fix, right? A little later. And of course, we looked at the, how can we make the decision boundary or decision making more accurate by increasing the width of the decision boundary. This is also called no man's land. Some professors use the term no man's land, like in a war zone. Right? No one should enter that. The area between line of actual control between 2 countries. So how can we maximize this gap so that our decision making on all in any given data sample set, our predictions would definitely be more accurate. Calling either side of these two in case of parallels. Also, deriving the distance between these two parallels, essentially considering each boundary as one line or a hyperplane, the distance between them, this equation is this, and this equation is applicable as well for not only 2 dimensions, but for multiple n dimensions as well. Like that. And we've defined and understood, essentially we understood the definitions of the maximum margin and the support with the hyperplanes. What are the support vectors that fall on these boundary lines, which line is nothing but a formation of vectors in a particular order. In case of linear formation, it is a line or a hyperplane. That is what we have used to derive the maximum width or margin between these two boundaries. We looked at that, we derived the mathematical formula for the distance, which is 3 by norm A, which is level 2 norm, right? And then we have used existing concept and the notion of optimization, mathematically optimization, and we formed or we have correlated the distance equation that we derived to express the formula or the formulation, mathematical formulation to maximize the distance so that we can solve for the weights vector A bar and then the B, the constant. And we've looked at the various names of the various components of the optimization formulation, the convex function, objective function, constraints, constraint optimization. The overall this problem is called constraint optimization. And we also looked at and understood the definition of the convex function. This is very, very important. It's a basic building block in mathematics. Convex functions and concave functions. But the opposite of convex, we use it concave. So try to understand these, visualize them and understand the intuitive meaning of these while having mastered in mathematical expression of the convex functions, because they are the critical components of your loss functions or loss optimization. Also, we intuitively really looked at what is a convex, what is a non-convex function. And then we looked at most assorted, which is considered the most complex concept called dual optimization. Step by step, we went from a final problem of an optimization, then we derived a Lagrange function, or also called Lagrangian, and then we have looked at the minimizing the Lagrangian, which is denoted by phi of Lagrangian multipliers, and then the x, considering Lagrangian multipliers as constant, which is called essentially the minimization or infinium of dual function. Infinium is the other name for minimization. These are all again basic building blocks. We look at the dual function, essentially that's a dual function, and then we try to maximize the dual function, which is nothing but the dual problem, and which is stated, the dual problem is stated. So this is related to the final problem, and maximizing that phi is the dual problem. And then we use the dual problem or dual formulation to solve for, are we solving for at the end of it? We are simply solving for A bar and B. B is a dual SVM. And we have looked at visual, intuitive understanding of what is the final problem what is the meaning, or what is the notion, what is the intuitive understanding of minimum of primary problem, and then the maximum of real problem. And we look at the strong duality, we look at the weak duality. Strong duality is when the primal minimized value is same as the dual maximized value for both the combination, where the variables are different. Right? We obviously, you must have seen, I have published these slides already onto the Google Classroom. You must have seen the derivation of it. I've skipped a couple of obvious steps of, like how do you arrive at this value? This is straightforward. Taking the first derivative and then calculating it and solving it. But this is overall solution for a dual optimization problem. It would be very, very important to understand this. So spend time leisurely and take the help of ChatGPT and Cloud to understand this. And then, of course, we also looked at can the SVM, how can we use SVM to solve classification or to classify data which is not necessarily linear, which is a non-linear SVM. We looked at the notion of ability of most of the data sets that had non-linearity in its current dimensions, but when transformed into higher dimensions, it is possible that they may have linear separability in the higher dimension. That is the key notion behind the usage of SVM for achieving linear separability for a non-linear data in the given dimension. And to achieve that, we've tricked it. Essentially, that's why it's called a kernel trick. We've tricked the data set by transforming into the higher dimension without actually computing the entire higher dimensional data space, but by using mathematical pretty formulations of kernel functions, mathematical kernel functions, right? Like these, to compute only the dot product, because at the end of the day, what we need is the dot product, irrespective of the dimensions, because the formula remains same. Only thing we have improved, increased the dimension, and all we need is a dot product. To compute the dot product, you need to have each data in the input also transform how it gets transformed each data point in the higher dimensional space, a lot of quantities. Hence, we use the trick of existing kernel functions to transform the data into higher dimensions, thereby helping us get the linear separability to classify the data. Essentially, that is a kernel trick, kernel method, right? These are most esoteric or complex notions. I tried my best to put them or to peel them off into as easy as possible, like a diamond. And I hope that you guys, most of you, are able to comprehend and understand and follow and appreciate the trick that is being used and why it is called kernel trick. We looked at that. And of course, we looked at some of the common kernel functions. Linear kernel, it's linear, there's no trick, it's straightforward. Polynomial kernel, essentially a degree of D. So this is also called degrees of freedom, the order of the polynomial degrees of freedom. Because those are the free variables or free directions that are controlling the data in that space that we are observing. The world, each individual is a specific variable. If you look at world comprising of 7+ billion people, this mostly have 7+ billion dimensions. And each person thinks in his or her own way, and if given a problem, the solution potentially could be thought through in 7 billion dimensions, 7 billion dimensions. So also we looked at, we try to understand essentially, this is nothing but Gaussian distribution, right? What is Gaussian distribution? e to the power minus 1 by 2 sigma square x bar minus mu bar. Right? I think here you have a constant 1 by 2 pi sigma square. So the radial basis function essentially is a Gaussian distribution, meaning it represents data. This is a mathematical formulation of a data set that exhibits a standard normal distribution, bell curve, essentially. So bell curve is there. By the way, bell curve used to be used by pretty much every organization in the world, by HR department, in identifying performance algorithms. The bell curve essentially says, this is your nearest mean, which usually is not more than 10 to 20%. Right? The rest, let's say 60%, that is 30 to 30% are average performance. This 10 to 20% are top performance. And 60% approximately are median performance. The rest, probably around 10%, are the bottom performance. 5% this side, 5% this side. So they used to take all the appraisal data and then plot them and then essentially follow this pattern. Don't give beyond the 10% top performance rating and 60% or 70% average and the rest bottom. Usually bottom is 50%. So these distributions are, you may not know them, they are used everywhere. So any mathematical formulation describing a real world data is a super important asset that you as an AI or data scientist, science engineers should be proud of, because that can generate value, money, career, or it can even impact the human society. Right? So this is a standard normal distribution in a radial basis function. It changes a little bit. It's like a bell curve, but there are certain variables. We looked at boundaries. We looked at the decision boundaries, and we looked at the kernel tricks versus PCA. Kernel trick appeared as if the inverse function of PCA, the final component analysis, where we reduced the dimensions. In case of kernel trick, we enhanced the dimensions, the transformation. And I also try to share with you, which I felt is of more relevant is the term used in algebra, the kernel space, which is mathematical null space of the matrix. Right? Matrix is the transform, null space is essentially that area in the original domain. These are all domains. That area in the original domain that translates or transforms to the same value or same space. In this case, this space is a dot in the transformed domain, right? And this, in that case, is called kernel, because it is behaving like a center origin of the transformed space. Hence, it's a kernel. Null space is a kernel. It's nothing but the origin in the mathematical form. Null space of the transformed domain. Right? And of course, the rank of the metrics which are used for mathematical computations of machine learning, the dimensions, dimensionality. And the null space is used in the rank nullity theorem to compute the dimensions. So I think we've stopped here. We'll spend 5-10 minutes and we'll spend the rest half an hour at least on the project. So another 15 minutes, we close this theoretical part of it, right? All right, so slack variable, SVM with slack variable. So what are slack variables? So what actually is slack? Let's try to understand the English meaning of slack. Anyone speak or type? What is the meaning of slack? No one? Slack is in a way not being firm, right? Let's say if you're disciplined, you're considered firm. But if, let's say, you're not disciplined and it's like a loose can, then slackiness, laziness, being also flexibility. It's not firm, right? So slack in our case refer to those data points that fall in the no man's land or in this margin, because we're not sure to which class we should classify if a data point belongs, falls in this fringe or margin or in this gap, right? These are slack. So we intentionally, to account for such slack data points, because then we won't be able to accurately predict. So then we know that this is like a noise, and we know that such noise obviously exists in the real world, and hence we have to account for it. So we account for it by introducing slack value. That is what SVM slack value is called. So essentially, the margin is hard when there is no slack, when we can achieve this gap without any data points falling in there. But real world data is not. There always will be boundary cases, and then, a red line, red dot falling in here, let's say, and a blue dot falling here, which you can see here, right? This is noise sometimes. Nothing is perfect. There's a lot of it. So to account for this noise and overlap, slack notion of slack variable. I think this is called C. This is a Greek letter, and on the C sounds like epsilon or A, right? C. C, right, is introduced, and that is nothing but it's like a correction to your notion, your optimization problem. Some variable in all dimensions with some constant minus. That's it. That could be plus or minus. So that's the formulation to account for that real world noise of overlap using the notion of slack variable. You have to add or deduct somewhere, and that is nothing but you see, and it's some constant always, because we want to have the flexibility to control hyperparameter, have to have a controllability. Of course, subject to, and this is important. This is where we introduce yi. Yi could be -1 or 1, and it should be greater than or equals to 1 minus. If you derive this from the primal problem, you can easily see that's going to be that C. And C has to be greater than 0 for input, because we know that 0 means what? There is no data point in this margin, but this is not the case. Our intention is that there would be slack. Hence, it has to be greater than or equals to 0. 0 essentially we want to achieve it, but it cannot be made. So that is the whole idea. C is a regularization factor, a control factor. Is a point either side of the margin. Essentially, it is a misclassification factor. So it gives us the flexibility for both linear separability and nonlinear separability. Even if it is a curve like this, we can have trenches both sides, right? And then we can introduce the slack variables to account for the data points in this area, right? So that's the slack variables. So then the accuracy. All of these you already know. So let's just try to put it down. Accuracy is nothing but the prediction accuracy. How many true positives and true negatives? And divided by true positives, true negatives, false positives, false negatives. So the total set, right? That is the accuracy. So this has to be 1. This has to be 1. You can easily see that these two have to be 0. False positives, false negatives have to be 0. That is when our prediction is done. When these two are 0, it's Pp plus Pn divided by Pp plus Pn, which is 2 positives, 2 negatives, plus false positives plus false negatives. Let's say we have PP plus PM. Let's say we have trained the model and we tweaked the variables such that PP, TN is whatever it is plus whatever the value that we achieve. False positive is 0 plus false negative is 0. So then these two are 0 and it's PP plus TN divided by PP plus TN, which means our accuracy is 1 in terms of the percentage 100%. That means it's perfect. So that's accuracy. The precision. What is precision? The samples predicted as positive or actually positive. So how many true positives divided by true positives and also whatever we have predicted as positive, but actually may not necessarily be positive, which are may not necessarily be positive or false positives, true positives or true positives, and obviously true positives. So this precision will be 0 when our false positive prediction is 0. And then the recall measures, we also had the other parameter, precision, and this is specificity, or sensitivity, one of those, right? Where they can have true negatives divided by true negatives plus anyone false negatives. It has to be 0. And then we have a recall, how the actual positive samples were correctly classified. That happens when two positives are divided by, we can achieve that number or that rate or value, two positive plus false negative. False negative has to be 0. False negative is essentially negative. False negative is a positive. So that is a recall. F1 score, we looked at essentially the harmonic mean and precision of recall. So we looked at formulas, we derived at the formula, we understood the notion behind it. It's 2 times precision and multiplied by recall divided by precision plus recall. That is the F1 score. We also spent a lot of time on confusion metrics, essentially, where we plot the TPs, TNs, FTs, FM. And we also understood already the receiver operating curve and the history behind it, why we call it receiver operating characteristic curve. Essentially, the precision we call are plotted across all classification thresholds, right? And simply a boundary threshold. When you move the boundary, essentially moving the boundary is nothing but changing your A bar and B values. Right? The boundary is decided by weights vector and then the B. And of course, which feature is the last one? I think we looked at this in one of the early linear regression modeling for the projects. Which feature is contributing significantly for the model prediction? These are the accuracy metrics. We looked at the project. We understood what is the project, what is the data set, what needs to be identified, and then the history behind the data set that has provided. I hope some of you have a chance to look at these websites and these papers and had gone through it. It would be really helpful for you to understand. It would be dry when you read these papers, but you have to form a habit of spending more time in understanding and interpreting each line. If needed, initially take the help of students, ChatGPTs or bots to explain what each sentence means, each variable, each notion means. And that is the only way to gain mastery in any subject or any stream of subject. Right? So the implementation steps, these are actually copy pasted from the Jupyter file that I have provided. released to you guys yesterday in the Google Classroom. I have also shared the announcement with WhatsApp. So essentially, the first part till this is pre-processing, and then the next part is training. Yeah, training and essentially standardizing the data. And the last part is plotting into various plots. So essentially, there are three periods: pre-process, training the model and predict, and print some data and plot the various methods. Let's look at the code. Any questions? Ladies and gentlemen, so far? Any questions, guys? Let's see. It's full implementation, but it's a pretty cool. Well, let's do it with two parents. This part. So have you guys seen this file? How many of you seen this file? Can you type? I've seen. In the message, can you type, guys? All right, looks like you guys are not in a position to type. So let's go through the code. So these are the imports. Some of these imports are just carried from the previous project. Some of them may not be relevant. And you may be wondering why all these underlined orange color curly lines and then lots of messages, orange messages, error messages and warnings. These are, ignore them. These are from some of the plugins that I use to auto-generate the code. There are plugins that are available for visual code that can produce code automatically for you, inclusive of machine learning, Codium, etc. So some of those plugins are spitting out the warning message. So don't give around them. Don't worry about it. Yeah. So in some of these imports also I have miscarried, so they may not be relevant. So I would expect you guys to get rid of those imports that are not needed. For example, if you see here, this is kind of grayed out a little bit, even though it's in color, it's less than color. So which means I might not be, this code is not using the spill module from the image, right? Obviously true, because this is a shell code. There's no code at all, logic at all. So I have provided the comment what you guys need to be doing. It's like giving you the step by step and guiding you each step where I would expect you to put the code. Right? Now let's look at the actual preliminary code. Imports. This I try to use a virtual environment and then activate it. So you can see here, it's possible to maintain. I'm sure because virtual environment is there. Instead of taking a global libraries of the Python, you can only take those libraries that are specific to that virtual environment you have created. So you have to create a virtual environment. So it helps you to run side by side multiple versions of the same library if your code is using older version of a particular library, but you have installed globally the latest version, then you can come out of that predicament by using a virtual environment where the lower version would be stored as a dependent library for that virtual environment in a virtual directory wherever you create it. Here I created it in this project folder. And these are essentially nothing but your command line, shell commands of the OS. And you can issue those commands to the Visual Code itself in Python Jupyter environment by using exclamation. I have commented it. So if you have to execute, you have to take out the command, essentially. This is one of the tricks, not a kind of trick, but it's a trick in Python, right? So that you don't have to get out because from the coding environment. So some of the configurations that I'm doing. I would like you to use this whatnot, the applied AI and ML IPL industry projects like whatnot image programming is going to be habit for the rest of the sessions to use that as a whatnot for each plot that we do. And I've given a code. And I have given and I won't look to the code earlier sessions in the early sessions. So this code essentially, or this method essentially, function adds given any context of the plot, it will add the watermark image at certain zoom level with certain transparency and certain rotation and don't think I'm using the rotation and even the passing as a comment. Essentially creates an image box, which is bound the image. You are going to transform that image, right? If it is a rotation, you have to transform the box either by that angle at 45 degrees. Essentially, always it's with respect to x-axis. So it's an affine transform. So essentially, linear transform also is called affine transform. Affine transform is nothing but with an intercept and with a slope. Essentially, affine transform does not change the characteristics of your original data set or original domain. And also, I think, is also a convex function. These are very interesting fundamental notions that we take it granted. We don't know they exist, but we do make use of them in every line of code when it comes to machine learning. Every line of every model, every algorithm. Right? So when you transform the image offset and you essentially transform it, you create an image offset and the rectangle box to transform it and you annotate and change it. And you add it to the context of the plot. Yes. That's the context. You load the data. So there is no separate external data here. Data file. It is part of the scikit-learn, and you can load that using the dataset module. So dataset is imported somewhere here. Yeah, sklearn. Actually, sklearn is the old name. It's renamed as scikit, but the module is addition. Under the datasets, there are various sets available you can explore. You load this method loads the best cancer dataset, and then you separate them into. Essentially, you are labeling them. Output as Y, input as X. Input has around that 30 or 40 or 50 features. Once you don't follow. Then print the description of the data set. So this is again an attribute which is part of the standard data set of scikit-learn. And standardize the data and standardizing earlier because I'm using some plots to visually plot the input data before training the prediction. Obviously, you need to convert that data into data frame so that you can plot something using your code. And then I'm setting certain boundary conditions for display of the data so that it won't scroll to the next line. The same column or same line. When you see the same data, one line of text in one line versus one line of text in two lines, your comprehensibility varies. The first case compensability is fast and high. Right? And then we are also essentially getting target. Counting the total training set, how many inputs data samples are there. Then we're filtering them, how many features are there, how many samples have the cancerous, non-cancerous tumors, benign tumors, and how many have the malignant or cancerous tumors based on the result in the data set that had the wide variety essentially. And we are also counting the number of features and printing the feature name or column name. So this is the data description of metadata about it. Essentially was created for these papers, the human purposes. 569 sample data vectors, both in entire data set. And each has 30 features. Right? I think it's 29 last time. I don't know, there's one ID or something. Number of samples with cancerous or non-cancerous or benign, 257, and the cancerous, the breast cancer, malignant cancerous tumors in the breast, around 201. Here are the feature names, mean variance, other texture, perimeter, area. All these are a bunch of numbers, whether continuous or in category 2. I find that the diagnostics and predictions are all based on value against mathematics. Remember, mathematics is an integral and non-separable part of human life and society. And it is important, super important to get on top of mathematics. So this is a sample data set. So first to go, just to get a sense of the value. Some of them, for example, are in big numbers compared to the compactness level. Right? And the other one is the highest. You can also see them. And then, so this is essentially pre-distributed. So when you have data in, let's say, let's do this again. When you have data, say, where each sample has some value y and some coordinate one feature x, then you can plot into them. And it's easy and easier as well to visually see the distribution by plotting all, in our case, 569. How many? Anyone remember it? How many data samples, guys? 589? Where is this number? 569. Okay. But in this particular data set, apart from Y label, which is the prediction whether the person has the breast cancer or not, whether it's malignant or non-benign, different. We have how many? 59, 39? How many columns, guys? Anyone remembers? 30 or 29 columns. 30. So how can we plot 30? These are nothing but dimensions. 30 dimensions plus 1, which is the output. That means 1 point needs to be represented. 1 point of whether that person has cancer or not needs to be represented using visually 30 different features or dimensions. It's multidimensional. Dimension is nothing but one aspect. So obviously 2D graph that we have been using ever since we started school and we've been told to use X and Y is not sufficient. Forget about that being sufficient. We can't even visualize, 30 dimensions. At the most we can see and visualize these 3 dimensions, and probably some maybe 4 dimensions. I don't know. Somebody, maybe God can see all the dimensions with the exists. That's what they call. So, but we would like to see how these are visually preserved, right? So hence, there are certain distribution plots that exist to represent multidimensional data with some tricks. TSNE, the T-distributed stochastic neighbor embedding, is one such technique. So T-distributed, it's actually comes from student distributed based on a paper in the 60s or 20s by one professor, I don't recollect his name, to represent the same quest he had, like what I just described. How can we represent multidimensional data visually to see the distribution, to predict some pattern, to identify the pattern? At the time, there were no machine learning algorithms, no dimensionality reduction techniques back then, right? So it is stochastic. What is stochasticity or stochasticness? Random, right? So selecting random neighbors which have higher density, similar to what I talked about yesterday, colonies in Kurnool, right? Where the people, if you look at Kurnool on Google Maps, till which point? Till dawn, which part is Kurnool? Kurnool is the part where there is a high density of visual structures in Google Maps, which are categorized into colonies, after which there are sparse such structures, and which has the highest area combining all those colonies. Right? The same way, those are all colonies or neighbors, and they have randomness because these colonies are not formed as per certain structure or any guidelines provided by the municipality. Their layout were formed based on a lot of convenience of the guy who built that layout back in, I don't know, whenever, 1800, 1700, or 19th, even the new colonies that are getting formed. So this technique essentially classifies, combines all those random structures that have the higher density, all the neighbors, and embeds them as, being nearer or a class. That is essentially the stochastic, T-distributed stochastic, and it's distributed stochastic neighbor embedding. That is the picture that you see here. This is for the raw data, and this is for scale, standardized data. Right? You can see in both cases some pattern, and it has been reduced to 2 dimensions. Obviously, 1 dimension is whether it has the breast cancer or not. Well, that is a third. Color represents whether it has the breast cancer or not, but the 2 dimensions are essentially reduction of 29 dimensions to 2. Essentially, it's a PCA 29 to 2. Right? So you can see some sort of pattern here. Let's see if I can draw. I'm sure you can easily identify the pattern of colors here. Right? And also for the standardized data, since it is standardized, they all form in the neighbor area, but this curve that you see here is nothing but the dense areas in the order of, if you look at these values, so the dense areas around these values is what you would see in this plot belonging. So that's the T distributed stochastic neighbor embedding. And then there is the other one, which is called the parallel coordinates plot. As the name says, just a second, please. As the name says, right, all the dimensions or coordinates of the data set are plotted parallel. Right? That is what you can see here. So if you count these lines, parallel line, how many it should be? These parallel lines should be how many? Anyone? Type or just a second. 30. So no one is interested. So saying or typing. So these parallel coordinates. So these are 30 coordinates. Till this point. Lines may not be 30, but it is showing 30 values. It's fine. 3, 3, 6, 9, 10, 20. It looks like it's 30. Okay. And these are the values. Obviously, this is for non-standardized data, parallel coordinate, and this is for standardized data. So for non-standardized data, essentially, because your scale of the value has to go in thousands, because some values are around 3,000, 2,000 change, those coordinates that have 0.00 values, they look as if they have no values, but you can see here, if you zoom this, you can see here they are plotted here, and they would be somewhere nearby at my mouse pointer. Right? And the red and green indicate cancerous or non-cancerous tumors, benign or malignant. This is the other way to see, to visualize and intuitively look for some pattern or a multi-dimensional in the data set, sample data set. This is for the standardized data. So, anyone, why here we see such peaks and we don't see such peaks here, but we see data is really distributed, at least not unevenly. Any guess in the standardized data plot? Anyone wanna express that? You all know. It's just that you do not know. That is the reason. Anyone? Soumya? Check. All right. It is because 2 points. What happens when we standardize? What are we doing when we standardize or scale the data? We are centering the data. What does that mean? We are identifying the mean value for each feature and deducting that mean value from each data sample of that feature, and we're dividing by variables. So that means data that was spread, when you take out the mean value, they're all gonna fall within the variance level. That means the spread of this is nothing but the variance. Right? And it won't vary much. Because if the data that describes the cancerous tumor in 30 dimensions, they pretty much should fall within the neighborhood of the data set that describes the cancerous tumor, and potentially away from benign tumor. And that is the reason you see it is like zoomed up. Right? When we center it, it's like zooming, essentially zooming this way. Then the precision, then we are the last step. We are training, predicting, and plotting methods. Right? So I've used multiple classification models, different colors, and the decision tree, k-nearest neighbor. I kind of used a functional set approach to compute the training using one method. By calling one method, all the models get trained recursively. I've used the notion of recursion here, even for training and then predicting the outcome across various models. So we train, what is our split? 20%, meaning 80% train, 20% test. So we fit the data. Essentially, fitting is nothing but identifying the coefficients or the grades, essentially forming your formula and formulating your decision boundary formula. And then predicting y value and then the probability for the soft market. When you predict 1 or 0, it's hard. When you predict the probability, I think we talked about it in previous classes. Instead of 1 or 0, but we're getting the probability, which lies between 0 and 1. Softmax function. So it's a probability. Right? In case of non-real, it's a softmax. If it is binary classification, it's probability. So then you are essentially deriving the soft margin of the probability. And if it is more than 5, then we can say it's either 1 or less than 5, let us say. Okay? And then also computing the accuracy score, computing the accuracy score. Accuracy score is a method that's already implemented. And if you provide your test sample data frame and predicted sample data frame, it automatically computes the accuracy and gives you a single scalar value percentage. And then the other metrics, confusion metrics, again exist in methods. And false positive rate, true positive rates, we've done all of this already based on the test and predicted data. And then the receiver operating characteristic curve, area under curve, precision, record. Again, these methods already exist. You simply pass them test output or test predicted value and its probability. So the original value of the output in the test data set. That is what I mean, test data set. And then what we predicted. If it is not known, if it is known, don't pass it. I don't use it. It's a sort of boundary condition, right? Assertion. Ensure it's assert. Also called assertion check. Computer implementation, software program. Right. Any questions so far? Then we compute F1 score. And then the plot accuracy score curve. Of course, if there's no curve, there's no data, don't curve, just sort of ensuring that we don't end up plotting null value, or 0 value, which is a blank. Yeah. So we have the thresholds and accuracy scores. We are deriving from the accuracy score by these are the standard way of providing the forming the data for plot. And then provide the data for plot. Comparing metrics. So a quick map. We've done that in the past and I'm going to go over that. ROC curve. We've done that in the past. Precision recall curve. So this is against precision against recall. So we compute the recall, we compute the precision. We are asking you to plot this using the Python environment using the existing methods, right? Library methods. And the feature importance. Feature importance is that which has higher influence, which is completed, which is important part. A method that is implemented as part of the model, It computes the feature importance, the feature and its weightage, its meaning. That's what we see in the plot. F1 score. F1 score formula we've seen, and the method implements the score, which we have already completed, but here we are plotting. And then for all of the plots, add the watermark. And of course, make it a tight layout so that you can fit into the defined area of the plot that we have defined at the top. 26 by something. Where did we define? A 24 by some 5 times the model data value, length of the model. Essentially, count of the model. Count of the dates of number of samples in the data. So these are the formulas. This is also one of the steps that I have requested to be implemented to print out the formula for precision recall and F1 score. So as you can see, linear SVM for this data set, linear and non-linear SVM, which is RDF kernel, they're given pretty much the same accuracy, 97.37. It's fairly a good accuracy, 97.37. 2.63 is the error. It's not perfect, but it's more than acceptable. Others are not giving other kernels and other classification methods. The logistic regression is being 96. Not that far behind, but less than SVM. So obviously SVM is far better, superior. Superior. K nearest neighbor. Third, decision tree accuracy is less. Naive base is, in this case, is obviously forest. Random forest is very less. So for each of the models, so let's look at first the two. First one is a linear SVM, the confusion matrix. So in the malignancy, we've done a for the predicted, we predicted 2 as benign when they were actually malignant. That's a false negative, right? Or false positive. We predicted 2 as benign. If you see here, predicted benign, 2 as benign when they were actually malignant. It's a false, false what? False negative. It's a false positive, actually. If you consider benign being positive, it's a false positive. But in medical tests, it's actually lack of disease is called considered as negative. And existence of disease is considered as positive because you're testing whether the person has disease or not. You're testing with the notion that he has a disease, which is, if it is positive, that means he has a disease. It is negative means he doesn't have a disease. So here in this case, predicted is benign, which means it turned out to be negative. So it's a false negative. In case of benign, we predicted 66 as benign, but actually there is one more that was benign variance. So here in this case, we predicted 2 as benign out of 47 malignant in the training days. We have predicted 66 as benign out of 67 being benign out of 67 being benign. Right? So there could be a problem with this data as well. The data should be 300 plus. This is why we are getting only 100 plus. Maybe I want you guys to find out why did I Are you also getting the same number? Totally, if you count, it's around 120 plus. But earlier we saw around 359 or 69. Figure that out and let me know in the next session. Right? Right. So essentially, these are the curves. So ROC curve. So we obviously want false positive rate should be 0. True positive rate should be 0. The area under curve should be a spike. Right? Precision recall curve. Recalls. Precisions. We want both precision and recall to be high. So it should be somewhere here. The feature importance, not much here. But I think only one model of algorithm provides feature importance. F1 score, it's almost touching 1. Accuracy score, we saw 90 something, 96.6, 97.37. But when you change the threshold, obviously it changes. So when you change the threshold, you are changing your A bar and then not B. Confusion metrics for the kernel, pretty much they should be same. ROC curve, they're pretty much same as we have seen. So let's try to wrap up. What is this one? Polynomial kernel. The accuracy was less. Naturally, your false positives and false negatives would go up. Right? And this is interesting to see here. Right? Everything is predicted as benign and perfectly. Right? These are all simple mathematical formulas. Right? We don't know. Actually, it's a disease and that to be careful. They just are given by examples. The other one is sigma-10, logistic regression. Accuracy was less. Decision tree. So in decision tree, so at each point, you would look at which feature has the highest importance. So if we are addressing this algorithm with time coordinates, you would understand that it's like a tree. You traverse each branch, and each branch you would compute a value based on certain characteristics. Which branch has a higher information entropy to take next. So because of that, we would be able to plot the importance. Entropy, essentially the information content, value of information content, is entropy. Simply put, entropy is nothing but the randomness of any substance. It also goes back to thermodynamics. Some of you might have studied in the first year in physics or chemistry, thermodynamics. The core part of the mechanical engineering reactions. Entropy is the randomness. So the more random an information is, less predictable it is, which means it has more information. That is entropy. Okay? Based on each feature, how much entropy each feature has, essentially is its contribution towards importance. Hence, so the worst concave points seem to be having highest entropy, highest contribution, randomness and contribution or information present to make a prediction in this case. Right? K nearest neighbor, so essentially it's something similar to the distributed stochastic neighbor. Naive base, again, it's not really so great. And then random forest, again, it's a forest, so you're traversing again entropy and information value at each feature or each line. So it is able to essentially they seem to be same with decision tree. I think values differ, but in terms of the correlation, right? Remember correlation? They seem to be correlated. You see the bar for the worst concave point, and yes, even here it's the worst concave point. And then, of course, plotting individually the relative graphs of accuracy, but in your case, these two models, linear and ROC, all those metrics that we saw above, plotted separately comparatively for both the models. and the decision boundaries. It's a linear here. It's a sort of bell curve if you look from left to right. It's curved, non-linear, and sort of a bell curve repeated. Two patterns of bell curve. And this is polynomial. That's one bell curve. It's like an S sigma. The decision boundary, right? Logistic regression linear. Decision tree. So it's tree tries to distinguish, right, at each feature point based on its information value or entropy. K nearest neighbors again based on the colony. So you can see zigzag with the colony as much as possible, but it can cover without overlapping. There is naive layers. It also has to be some sort of non-even. And the other one is an and policy, something like this. Even generated to be. Any questions, ladies and gentlemen? That's about SVM. Any questions? All right. Anything you would like to add, Professor Suresh, if you would like to?
No, sir, nothing, sir. Like, yeah, today's topic is very clear, sir, actually. So, like, I was just listening to the topic continuously.
Right.
Yeah, it's clear, sir, very clear. So, sorry, actually, yesterday I couldn't join the session because of some other meetings. So, we have a national level fest this coming week, sir. So, we guys are a bit busy in arranging those things and like that.
Excellent, excellent. My best wishes and blessings for success of the national fest.
Yes, sir.
SVM is the most, if you want to understand, it's the most complex algorithm because it touches across pretty much all the notions of mathematics, functions, non-linearities. I tried my best to peel that off and to make it as simplified as possible.
Yes, sir. It was clear, sir. The explanation was clear.
Right. And my intent is, for some of us, it took years after engineering to understand these esoteric concepts, complex concepts. But my intention and objective always is to use the principal component analysis of compressing those multi-dimensional complex data into a simple two-dimensional data for these students. That is my endeavor, and I hope some of your students are able to not only comprehend but appreciate that endeavor to take out the complexity and bring the simplicity into this concept. And I hope I am partly successful in that endeavor.
Absolutely, sir. Absolutely.
All right. Thank you, all of you, and wish you all the very best. Again, it's an involved concept. It touches across multiple nooks and corners of the mathematics, from optimization to various distributions to formulations of the distributions. So pay attention, spend more time, understand each notion. No one will understand when you read first. And if you read first and if you understand, usually that means either you have already spent sizable number of years or you are reading a novel. Even novel also sometimes it's difficult to follow. So it requires multiple reads, multiple passes. It's just like training, right? Machine level or machine learning algorithms, they don't get trained. The learning parameters, we don't derive the values and use them after 1 or 2 or 3 samples being learned in classes. It requires hundreds and thousands and millions of passes. The same way, if you want to become expert, you are no different from machine learning. You have to pass not necessarily million times, but multiple times to the same content so that you can understand. So with that thought, I would like to leave you guys for the rest of the week. Have a great weekend. Bye.
Thank you so much, sir. Thanks for the wonderful class and explanation.
Yeah.
Nice
Thank
day,
you,
sir.
Professor.
Thank you so much. Yeah.